The same religion that's capable of hideous acts of destruction can also be capable of moments of healing, of restoration, and of hope.
But educate a girl, and you educate her entire family.
There is a sun within every person.
When that anger sets in, write it. Write the letters, but don't send them. You never want to leave concrete proof of insanity.
I want to speak to you today about a couple of efforts that are going on here at UCSB, and I've sort of kept this at a very high level. It's easy to get down into the details. If you have questions, please stop me, but I thought what I would do is just trying to give you an overview. So maybe this is not obvious, or maybe it is, but in the high-performance computing realm, and my background is in this, from Livermore and Berkeley and so on and so forth, it's often the case that getting lots of computers together to do one thing is a good idea. It's often the case that it's not. Right? You wouldn't necessarily want your cell phone to have 100 computers in it, although it might someday. But that's a, that's a different matter. There's power issues and so on and so forth. And in the science community, in the engineering community, we have known this for a long time. But in the commercial sector recently, with things like the search engines, it's become true there as well. Google has a lot of computers, and they're all working on one thing at the same time: search. So you see, Amazon.com and Google and Ask.com and so on and so forth, as well as the things that we want to do in science and engineering. Molecular dynamics, nanotechnology, chemistry, astrophysics, so on and so forth, all requiring this kind of large-scale compute, which we really can't get out of a single machine anymore. And so this really brings to bear the idea of scalable systems. How do we build computer systems that can solve large-scale problems by aggregating power, right? Aggregating compute power from lots of different compute engines, if you will, right? And it's an active area of research. It's been around a while. What's interesting is that this year it's become a national priority. And that, for those of us who've been doing this for a while, is kind of strange. The President, in his State of the Union address this year, actually calls out supercomputing as one of the nation's strategic priorities. That doesn't mean quite so much as the fact that the Council on Competitiveness, perhaps, which is an organization that is advising the government, thinks of HPC as being really important to American competitiveness. Now, that's a surprise to me, right? If you were to take a bunch of computer scientists and ask them what's the most important thing to American competitiveness, they don't say supercomputers. They say the network, right? The internet is most important. Or they say security. Or they say graphics, all of which you're going to hear about today. But it turns out that HPC, apparently, has become something that America needs. And so, great. Here at UCSB, we've actually initiated or started a couple of different projects that really showcase UCSB's strengths in this area, and it's really an opportunity for UCSB, since not a lot of other universities are this well prepared to take advantage of this new or recurring interest in HPC. And I'm going to talk about two of them. The first is something that we've been calling the UCSB Grid, which is an effort to take the compute resources that are here on campus now, which are largely balkanized. They're operated by different research groups, each of which has a very specific and tightly controlled agenda, and tie them together. We would like them to be able to operate in concert, given that the idea that those resources are actually owned by individual groups who have to maintain local control. And so there's some software that allows you to do that. We're working on deploying that here at UCSB. And then I want to talk about the Petascale initiative, which is a brand new initiative from the National Science Foundation that has come out that UCSB will be responding to. Okay, so this comes under the heading of the Grid. It's unfortunate this term gets bandied about a lot. I'll just give you sort of the high-level conceptual view. It dawned on a bunch of us about 10 years ago that what we really want to do with computers is kind of what you do with power. All right? You want an infrastructure so that if you have a computer, a power generator, you can plug it into this infrastructure and give power or sell power to others who you don't know. Right? The power is going into the grid. And the same thing, if you have a program that's like an appliance, you want to plug it into this and draw power out. And notice that what you want to do is you want to move around where power is coming from. You will have to be able to disconnect certain power generators because they're, in maintenance mode or whatever, so on and so forth. There really is no software infrastructure that can make this vision happen. Now, we think of the internet, right? The internet as being such a software infrastructure, and it kind of is and it kind of isn't. The internet right now is a bitway. It transmits bits from one place to another. Most of those bits represent pictures. Right? Some of them represent voice. Occasionally, you put in little things like into forms and so on and so forth. That's not what it's going to do, but that's kind of what it does. This is more than that. This is a control structure. This is a way of turning lots of computers into a compute engine, right? And you need to do more than just move the bits back and forth, although moving the bits back and forth is important to make this happen. And it's got to scale, right? We want it to be running at national and international levels. And what's really key here is it's federated. If I buy a machine for my research purposes or for my company, and I want to plug it into this infrastructure, I have to be able to get what I need to get out of that machine when I need it. I need local control. It does me no good to spend $1 million on a machine and say, oh, gee, UCSB is going to go take 50% of it for the next 3 weeks, unless I want UCSB to have 50% of it for the next 3 weeks. And so there has to be structure there that allows this hegemony, this top-level coverage, and local control. Okay? And so we've tried, there's technology out there to do that, and our research group is involved in it. And we're actually initiating an effort here at UCSB to do this with CNSI, the Nanoscale Institute, computer science, chemical engineering, chemistry, geography, psychology, the various entities on campus that have resources that could benefit from this, and the instructional resources. There's a lot of instructional resources here that have compute power that's idle most of the time. Why? Well, the students come in and they do their email from like 11 to 1, and they have projects periodically, but the rest of the time we're just heating the buildings. And if we can use those resources without impacting the students, so they can still read their email from 11 to 1, it's a win. So, and that's here on campus. The other thing that we have is a lot of very special purpose devices that are being delivered here that need to be attached to larger compute infrastructure, right? So people are doing SensorNet research here. These things tend to be little installations of small computers, but you want to hook them to large-scale infrastructure. Something called a fog screen, which is a very interesting project that comes out of MIT. Tobias Hohler from Computer Science has really been investigating. This is sort of like a 3D holographic display that projects into gas. Right? Very, very unusual, but there's only one of them. And what you'd like to do is hook that to different kinds of things. The Allosphere is an immersive display that's being deployed over at CNSI, so on and so forth. And you also want to be able to interact with other campuses. So we're all involved in multi-campus infrastructure, multi-campus research. These are a couple of grants that I know about. There are lots of others, as we were seeing earlier. If you were to do this, if you try to pull this off just by hand, you drive your system administrators to the insane asylum. I mean, there are so many different infrastructures that you have to make work together, so many different machines. Often these machines are individually managed by graduate students, and that's a catastrophe, right? The very first thing you do once you get a system administrator working on your system and it's working is never let them go. Right? So you have this tension. You're making your graduate student keep your infrastructure alive, which your research program needs, and that graduate student needs to graduate. And when they do, all the institutional knowledge goes with them. Bad. So, but we spent a lot of money on the gear, and the university has and other people have, so we need to figure out how to make this happen. This is just a silly cartoon of what we're going to try to do as the first phase. Okay? So in the computer science department, we have about 200 nodes that we can devote to such an effort. They come in two flavors. Red are research nodes that live in clusters that are being used for research, and green are instructional resources in the student labs. CNSI has about 150 nodes in 3 different clusters, and there's a bunch of chemists, Joan Shea over in chemistry primarily, who run NAMD, which is a molecular dynamics code. And they run these things on about 30 desktops. And what we're doing is deploying the software fabric, sort of the thing that's going to make all of this kind of play together so that these people will be able to get access to those resources while these various stakeholders maintain control. That's being deployed now. We think it's going to work. In addition to that, this infrastructure links through the software to the national grid, which is operated by the National Science Foundation. It comes under the heading now of cyber infrastructure. Our primary point of contact here is San Diego Supercomputer Center, and to UCLA, which is where the other half of CNSI is located and where they have resources similarly. So in theory, these people will be able to access their resources, our resources, and resources out there. Okay, so that's the UCSB grid. Another thing that sort of dovetails with that is really the investigation of what's going to happen at the very, very high end of computing. So that ties together all the resources we have now. But there's an impetus now to build very large computers. And this is just kind of a current roadmap. I benchmarked that laptop yesterday. It's about 100 megaflops. That means that for floating point calculations, it does 100 million in 1 second. Okay? The servers in our labs do about 300 million. So a server that we buy from Dell and rack into the machine room is about 3 times as powerful. I talked to some folks at Livermore. This is about the top end of what you can get out of a single box, a single server today. It's about 40 gigaflops. It's 40 billion floating point operations per second. The fastest NSF supercomputer is 16 teraflops. Okay, so if billion is 10 to the 9, teraflops is 10 to the 12, right? And the world record holder is 280 teraflops. Where do we go next? Petaflops, right? 10 to the 15. But the key thing here is that you want this power to be delivered to a molecular dynamics code, or a weather forecasting code, or a chemistry code, something that needs some amount of power that comes out of that spectrum, right? And the belief is that brand new developments, new science, right, will come out of being able to go 1 order of magnitude greater there. This is just a picture of what the growth curve looks like in supercomputers. There's something called the top500.org. They measure fastest supercomputer performance of the top 500 machines in the world. The blue is the actual world record holder, and there's 280 teraflops. This is machine number 500, and there's your 40 gigaflop machine. So you'd make the top 500 in the year 2000, and in the year 2000, that machine was a very, very large machine with a single box today. About 7 years, right? This is a log scale, so that's just exponential growth. And maybe it's related to Moore's law, maybe it's not, but the bottom line is that the high end is getting faster exponentially, and we want to continue that trend. And this has essentially spawned a competition between the three of the 4 major funding agencies. Department of Energy has always been a consumer of large-scale flops. And they've actually just deployed a machine called Roadrunner, which theoretically has a peak performance of 1 petaflop. Nobody who takes this seriously thinks that they're going to get above about 500 teraflops on anything real. So it's a nice idea. It's an interesting machine. It certainly is going to go fast, but it's not going to reach a petaflop. DARPA funded a 10-year effort, which is going to come to a close in the year 2010, to get vendors to build and deploy new architectures to do this, and they've been downsampling or down-selecting. IBM and Sun are the 2 remaining players, and they think that they're going to achieve a sustained petaflop by 2010. NSF has just decided that they're going to beat them by a year. They're going to leverage all that research. The key thing for NSF, though, is you've got to have applications working. It can't be a benchmark, right? So, and what are the applications? Well, they call out some. Nanotechnology, astrophysics, molecular dynamics, the usual suspects. This is such a big program that the entire University of California, not UCSB, but all of UC, is responding, and their pre-proposal has been selected. Here is the slide that I got from the program, the PI, Fran Berman. And all it really says is that in order to make this work, you need the state of California. This is good. You need scientists to do experiment. You need theoreticians, scientists, and the hardware. Okay? So, but I mean, there's more to it than that. Really, it's the idea that you go through this cycle of experimentation and theory, and then simulation, large-scale simulation, sits in the middle of this. Okay, so this machine is going to be between 400,000 and 1 million processors. Okay, that's a lot. 1,000-node cluster is what the people use at Santa Cruz to do genetic sequencing. 1 million nodes is bigger than anything we've ever seen. It's somewhere between 10 megawatts and 30 megawatts of power just to run a calculation. That's a power subsystem, right? It's not It's not here on campus. So, and so there are some site problems. But even if you solve them, we don't know how to program such a machine. We really don't know how to get codes to run at this kind of scale. It turns out that if you want to go from about 10 to the 2, about 100 processors, to about 1,000 processors with most of these codes, you can re-engineer your codes. It takes man-years. If you actually look at the effort to do that, it's measured in man-years. And we need to go to 10 to the 5, 10 to the 6 processors. That's bad, right? If one order of magnitude is man-years, how do we go from 10 to the 3 to 10 to the 6? We don't know. And really, so there are these applications questions. There are systems questions. Google, well, they don't tell us, but we suspect, is operating at about 10 to the 4 machines, no problem, right now. Maybe 10 to the 5. We're not sure. They have tremendous problems with their system software. And there are a lot more resources available to Google financially to solve them. So this is essentially a moonshot, right? We're trying to get to the moon by 2009. That's a good thing. To get to the moon, UCSB is uniquely positioned, really, because it's not going to happen unless there's a vertically integrated team, unless there's a team of people who are doing the computer science, the computational science, which is sort of the numerical methods, the actual science, right, the scientists, all working together to figure out how to make this brand new device work at that scale, right? And very few campuses within the UC system have that kind of interdisciplinary expertise already plugged together. I mean, I think what you're going to find while you're here at Engineering Insights Day is that there are all these teams of people, right? I was just sitting in on the fluids talk before this talk. It's not one research group. It's a team of people. And those people include industry. And we certainly would like to include industry in this effort. So you have this unique opportunity here at UCSB within the UC system to help respond to this $200 million NSF proposal. But the first thing you're going to want to do to this thing is you're going to want to hook it up to your own computers, right? A petaflop is, of course, not enough. The UCSB grid effort kind of ties this all together, which means at some point, we're going to get to exaflops, and I will stop there.
Okay, so why are web applications important? Right, well, they're ubiquitous, you know, as an application delivery medium. They're easy to develop, deploy, and access all over. So what the result is that these applications are pervasive in the sense that every company, agency, person tends to have a web page. And in fact, sometimes you have web pages that you wish weren't out there, such as if you go to NSA.com instead of NSA.gov, you get a porn site. Okay, and so that's not so good. They're critical in the sense that they sit as a front end for sensitive information that's behind it. Behind it are these databases that have health information, financial information, bidding information of the company, and so forth. They're open. Everybody's got port 80 open, so anywhere on the internet you can be sitting over in Cambodia accessing a web page here in Santa Barbara. And they're dynamic. They seem to be changing all the time. They change quite frequently. Combined with all of this is that who winds up developing your web page? Generally, for all of these back-end devices here, the database and so forth, they're developed by people who have some security expertise, care about security, and so they're reasonably secure. I wouldn't say they're secure because we have a business making sure they're not secure. Okay, but they're reasonably secure. But when you want to do your web page, what you want is the person that makes it look good, makes it friendly. And generally they have very little knowledge of security. And so you're putting this very weak front end on your secure back end. So the result of this is that there's a bunch of web application attacks. And I'm not going to talk about any of these, but I'm sure you've heard of buffer overflows, cross-site scripting, and so forth. And we did a study 2 years ago, or about a year and a half ago, where we looked at all of the vulnerabilities that are out there. More than 25% of them were web-related. And Symantec, one of the leaders in this field, one of the commercial leaders in this field, just came out with a study in September where their estimate was closer to 50%. The result is that where are the hackers going? The hackers are all going to your web-based applications, okay? And so it's a very popular target for hackers these days. What that means is that those of us who wear the white hat have to make sure it's all protected for you. You know, it's this game, where are we going next? Okay, so our approach to dealing with web application attacks or to security in general to try and prevent security is something we call intrusion detection systems, or IDEs. And what these intrusion detection systems do is they examine time-ordered stream of events. Sometimes it's a single event. Generally, it's a sequence of events. If we're doing it at the network level, we're talking about having a network sniffer, and we're looking at all the packets going across the network. At the host level, we're talking about system calls or audit records. At the application level, we're talking about syslogs, HTTP access logs, and so forth. And in particular, I'm going to address the application level. When we talk about intrusion detection systems, there's two types of intrusion detection systems. There's misuse detection and there's anomaly detection. We did a lot of work in the 90s and early part of 2000 of this century on misuse detection. And the idea of misuse detection is that you take known attacks, you look what they look like, what is a signature for this attack, and you develop that signature, and then you look for it to happen. So for instance, if it's on the network, we know that when this attack happens, we'll see a packet that looks like X, followed by a packet that looks like Y between those two. We write a signature for that. Whenever we see it, we raise a flag, say alert, either drop the connection or send a signal back and burn that person's motherboard or whatever we want to do, depending on how involved we want to get. Okay? It's got very little low positives. When it says an alert, it usually is an alert. It's got poor generalization. You write the signature, variations on the signatures may not be caught. More importantly, new attacks are not caught. Okay? Anomaly detection handles the other side of that. Instead of modeling what bad behavior looks like, anomaly detection systems model what good behavior looks like. And so it says, this is what we normally see. And then whenever we see something that's abnormal, we raise an alert, say there's a problem here. Generally on anomaly systems, we didn't send that signal back and fry your motherboard. Why not? They had a lot of false positives. Okay? And so this is the area that we're currently working in. And we're using a particular approach to anomaly detection called learning-based anomaly detection. And the idea here is that you generate models of what normal behavior looks like, and you have to do this on a history of attack-free samples. And then these models are associated with a particular domain, and they're limited in scope to samples observed during the training period. So one of the problems with this, remember I said the false alarms, suppose we're training for 2 days or 2 hours or whatever we determine is the appropriate amount, maybe 2 weeks. If it turns out that in that 2 weeks there's a normal behavior that did not occur, well then that doesn't become part of our model. Okay? So then if in the next week when we go into detection mode that normal behavior comes, we're going to raise it and say, boy, there's a problem here. Okay? But we have ways of dealing with that so it doesn't happen as often. It's got the potential to capture tighter installation-specific behaviors because it's learning, it customizes itself to your particular situation, to your particular site, and so forth. Okay? And as I said, it's building up patterns of user behavior. So the basic approach has 3 phases. The first phase, we take some training set, which may be data that we've collected, or it may be that we're just running live on your particular system. And with this training set, what we do is we use our learning models and build up a model of what's normal behavior. The next phase is to say, how much of a deviation from that normal behavior can I have before I raise an alert? This is the way we can take care of some of the new behavior. And the result of this is that we develop some thresholds that say at what level do we want to alert. And then finally, when we go into detection mode, we're using those training models. And we say, gee, it missed the model, but it didn't miss by enough, so it's probably okay. Or it exceeded the threshold, and so we raise an alert. Now, the particular thing I want to talk about today is web anomaly detection. And what we're doing here is we're examining the web requests that the client sends to the server. Okay? And when we're doing this, an example request here is a CGI request here. And what we do is we apply statistical methods to each of the attributes and each of the values for those attributes in two phases. The learning phase that says what do they normally look like, and the detection phase. So the idea here is that we are looking at a particular application, and you can think of this as the application that's running, that puts a form up on your web page, and you say fill these things in. Username. Username, for instance, is going to be characters, probably all character. It's probably not going to exceed 25 characters in length. Okay? And so when we see something else that contains things other than characters, or it's too long, what we're going to do is alert to that. So we do it for each application. We also do it for each of the parameters, each of the attribute names here, which is the ID and then the file. And for those particular things, the ID here is going to have a different value, different types of values than what the file is going to be. The file is going to be a mix of characters, a slash, a mix of characters, maybe a dot in there, but you're not going to see other sorts of things. So we deal with things like string length, if it's a string, character distribution, structure. And so, for instance, structure and character distribution are going to show up in that last one. String length probably in the first one here. This may be even what we call a token. If there's a minimum number of these things, then we just say these tokens are the only ones that are allowed and so forth. So that's the attributes, and then we look at the values of each of the attributes. And as I said, we have the learning phase and a detection phase. So for our particular model, what we're doing is we're doing these seven different models that we're looking at, and I'm not going to go into the details of all of them, but I'll just show you a little bit about the first two. For the length model, one of the observations is that for a particular attribute, it usually is either a fixed size or it's within some small range. Okay? And so what we do is we try to approximate what the distribution is by looking at all the things we see during the training phase. And then we use some weak-bound results which give us the tolerance we want. In particular, we're using the Chebyshev inequality here. L in this case is when we're in detection mode, that's the length we see. This is our length, our average length that we're looking for, and then this is the normal variance that you get. Okay, so it's just a different form of the Chebyshev inequality. For string character distribution, what we find is that the characters will, when you're looking at just the count of the number of characters that you see in each of these requests, then they're going to fit some model. Now this doesn't say A or B or Q has to be high like this, but what we're doing is we're looking for a fit to this. So when we get something where it's flat like this, an even distribution, or it's one or two characters and then a fast drop-off, okay, we know that's anomalous. Okay, so the character distribution just models the idealized character distribution, which is called the ICD, and then the anomaly score is calculated using a variant of the Pearson chi-squared test. And we have a number of papers on this if you want to get some references from me later. Okay, so what happens is we've got, in this case, 7 different models that we're working with. Okay? Now, I should mention not all of these models will apply to every attribute. Okay? Particularly the string models where we're talking about length and character distribution, those will apply to strings, but they won't apply to some of the others. Okay? So what we want to do is we've got these 7 values, and we want to combine them some way and get an alert score. Right? So the simplest way of doing that is something which is called naive Bayes, or naive Bayesian approach, okay, which means nothing more than sum them up. Okay? So if I alert at this value here, I just sum them up and get a high value. What it turns out is that is a naive way of doing it. Another way is just doing a weighted sum, where we say, for instance, an anomaly in character distribution is more important than an anomaly in length and so forth. But what we find is that if one feature is anomalous, this often says that we should expect anomalous behavior in another feature. Or if it's anomalous, it says, gee, we shouldn't look for anomalous behavior here. So there's actually a relationship between these models. Okay? So these dependencies can be represented using Bayesian decision networks. And just to show you a simple example here, one of the things that affects where there's a definite relationship is in string length. If the string length is small, the character distribution's quality is probably null. Okay, doesn't work very well for short strings. On the other hand, where we have long strings, it definitely affects the character distribution quality here, and it says we can put a lot of faith in that. Character distribution also affects the structure quality and so forth. The token finder, which is the token finder, is when we only have a finite number of values for something. So, for instance, the field might be asking something like month. Okay, well, we only have 12 possible values there, and anything else we alert on. That doesn't really affect any of these others here. It's really independent. Okay, so when I asked what I should talk about here, how much time do I have? You have 6 minutes. I have 6 minutes. Okay. Let me go back up there. All right. I want to say a couple things, which I didn't put on the slide here because I thought we were doing 15 minutes and not 20. Something else that we've done here is we've got two things. I said we're going to deal with false alarms. So one of the things that we did is we've developed something that we're actually in the process of patenting now, which is called an anomaly signature. Remember, for misuse detection, you had a signature that says, when you see this, alert on it. On anomalies, it says, I see something different. In most anomaly detection systems, when they see something different, they just say, oh, it's anomalous. And it might say because the string's too long or because of the character distribution, but it doesn't tell you any more. Okay? And you might see hundreds of these or thousands of these. So one of the things we've developed is this thing called an anomaly signature, which I don't have a picture of, unfortunately. And the anomaly signature says, when I get an anomalous alert in, I say, have I seen one like this before? Okay? And by one like this says, what models is it alerting in, and how is it alerting? You know, how is it anomalous? Okay? If I haven't seen one like that, then what I do is I go and I say, oh, let's define an anomaly signature for this. So we say it's anomalous in this way. We apply some generalization algorithms to it that says it doesn't have to look exactly like this, but if it's similar to this, we'll say this is another one of that kind. And so we define an anomaly signature, and so now if we get another one of those, we're saying, oh yeah, that's the same as that group, put it in the group there. The idea there is that instead of presenting the site security officer with 200 alerts, or 2,000 alerts, but let's go with 200, we might have grouped 97 of those. We say these 97 all look the same, these 98 all look the same, and here's 3 individual ones. So now they have 5 things to look at rather than 200. Okay. We've also done some heuristics where we're actually labeling those, where we say, you've got these 97 alerts, and it looks like a buffer overflow, or it looks like cross-site scripting, and so forth. And so we have a number of those too. Now, okay, so when I was asked what I was supposed to talk about here, they said, okay, there's people from industry, there's people with money, and so you should talk about things like technology transfer. Okay, so we're doing technology transfer on this. We've developed a product called WebLock, and it's a web application security module that ISVs can integrate into their web-based offerings. The idea that is that what you get from Microsoft, okay, or what you get from PeopleSoft and so forth is going to include our IP. So it detects and reports or blocks attacks. It does generic, which is signature-based, as well as our anomaly-based technology. It's sophisticated in that it customizes itself to your particular website. It does aggressive reduction of impact on false positives, what I've just defined. And all you need to do is just drop it in, and it does its own learning. Okay, does this sound like a sales pitch? Okay. The WebLock module can either set in your web server, behind a firewall, or it can set as a separate appliance.
So I'm going to try to give you a little different view on things than the past 3 talks. I'm going to involve people in this talk and how people interact with computing in various ways. And because I'm standing between you and lunch, I'm going to try to show you some images and video and keep you somewhat interested while your stomachs are rumbling. What do I do here? There you go. So a little bit of background, big picture, forest level background first. Computing has changed over the years. The function, the form, the context of computing have all changed quite a bit and are in fact changing, I think, fairly rapidly. And what I mean by that is the things we do with computers have changed a lot. We don't just use them to do word processing and spreadsheets these days. The form of them, the little devices that we carry or wear, the huge things that are woven into the buildings and all around us are very different from just these boxes that sit on our desks. The context, the applications, the things we want to use computing for are very different than in the early days or even from 5 years ago. These things are changing quite a bit, and related to that is the idea that the central data elements of computing have also changed from, in the early days, computing being basically about numbers, and then about numbers and text, and then about numbers and text and images, and then adding audio and video and 3D modeling and all sorts of things. The array of things that we compute on is very different than it used to be, and it continues to change. And basically all the data that underlies communication is data that is really fundamental to computing these days. And so the question that I'm interested related to this big picture is how does these sorts of systematic changes, how do those things affect the ways we interact with computers and computing in general? So putting the human in the picture, how do we most effectively communicate to and with computing in various ways? So we can sort of look at a historical view of this. Evolution of user interfaces over the histories. We started with sort of switches and then punch cards and command line interfaces focusing on text primarily. Finally, graphical interfaces, which in fact at first only focused on text, and then we brought in images and other things. And so there have been sort of a few generations of human-computer interaction models or paradigms that have, and the last one, the graphical interface, has been around a long time, and it's very powerful and has been very useful in many ways. But you can ask the question, with the changes in computing, what is or might be sort of the next major paradigm, or at least directions in which we might be going, where the graphical interface might not be sort of the main way or the only significant way we interact with computing in the future. So where are we headed? Well, we get some ideas of where we might be headed from popular media and movies and such. The ideas of talking to a computer, the ideas of gesturing to a computer, of plugging in directly in various ways to a computer, and of having computers that are intelligent enough we can just talk to them and sketch and all sorts of things that they can understand. You know, in some ways, what I do and what a lot of my colleagues do are driven by science fiction movies because it looks cool and, hey, maybe we actually could do that sort of thing. And in fact, we can do some of these things. So, you know, I'm not embarrassed to say that I'm motivated by funny movies. But where that takes me as a professional is that in order to go towards this kind of goal of developing powerful, adaptive, compelling interfaces that go beyond the current graphical interface and the keyboard and mouse and display that we tend to use in our offices, what we need to do is to develop and integrate a bunch of technologies that, from my point of view, are focused on sensing, display, and interaction. And so all these sorts of things, you're probably all aware of some kinds of activities going on in these areas. Speech recognition and natural language processing, of course, is very well known. This column here are really the group of things that I in my lab focus on primarily. Computer vision, graphics and animation, visualization, augmented reality, to some degree haptic I/O, which is touch-based, force feedback kinds of things, tangible interfaces, interfaces that you touch and manipulate physically rather than just with a mouse or something. So these are all things that people are working on, and in our lab we're particularly focusing on these with the goal in mind of developing, again, powerful new kinds of interaction technologies. Okay? So that's sort of the big picture. So the Four Eyes Lab, the lab that I co-direct with my colleague Tobias Huller, exists to go towards that goal. Okay? This big picture of more natural and different ways of interacting with computing. The name of the Four Eyes Lab actually comes from these 4 words: imaging, interaction, and innovative interfaces, that essentially are the motto of the lab, or the research areas in a general sense that we're interested in. And of course there's the play, the pun with 4 eyes and all. We're about 12 students and visitors and a bunch of 12 PhD students and some visitors and a bunch of masters and some undergraduate students. And the primary research areas of the lab, again, are vision-based and multimodal interfaces, augmented reality, which is this general idea of augmenting the real world with extra information, and I'll show you an example of that in a minute. Wearable and mobile computing, so computing that is always with you. You're either wearing it or carrying it with you. 3D graphics, interactive multimedia, and other related areas. So you can go to the lab sometime and our lab website and look at a bunch of projects and get a little better picture of what we do, download papers if you're interested, etc. So in general, what we want to do is to provide better and more compelling human-computer interaction technologies in a variety of computing environments that are important. Desktop computing still is very important. Immersive computing in various ways. Virtual reality and other kinds of immersive systems. Mobile systems, augmented reality, ubiquitous computing, all these sorts of newfangled environments that historically have not been a big deal in computing but are nowadays. Also for a variety of application areas, for scientific applications, for entertainment, for information visualization, for collaborative kind of applications, a wide variety of application areas that we're interested in. And so we're really investigating fundamental issues to develop robust and real-time systems to apply in these areas. And again, these are sort of the main big picture technologies that we're interested in: computer vision, computer graphics, human-computer interaction. So that's kind of very briefly a bird's eye view, big picture of what we're trying to do, what we're interested in. Now I want to just give you a sampling of a few of the projects that we're involved in the lab, just to give you a feel for the details of the kinds of things we do. One project is called HandView, and this is in the context of an augmented reality environment. Here's a person who is walking around the world wearing a backpack with some sort of computer in there and a head-mounted display that lets her see through that display, but also see graphics that's overlaid on her field of view. Okay, so if I had that on right now, I could see all of you, but maybe there'd be text going over each one of your heads that say your name, that tell me who you are, or that point out where the faces are, or something like that, or point out where the bad guys are, or who knows what. Here's another version of an augmented reality system that's much less intrusive. On her glasses, she just has this little device on the side, and it's basically projecting graphical information into her field of view. And she has a much smaller computer that she's wearing. But the general idea of augmented reality is that in some context, you have a system that is, in this case, visually augmenting your field of view. It could be through sound, it could be through other ways as well. Also in this system, there's a camera up here, a very small camera that's looking out in front of her, which might be used to relay information back to the home base if she's a search and rescue kind of person, or a scientist out in the field, or whatever. Or just something that you're using to take pictures as you walk through the streets of Paris. But we're going to use that camera particularly to track the person's hands, to understand some basic gestures and postures of the hands, and use your hands as a way to interact with the computing system. So basically driving a computing system as you walk around the world without having to carry a mouse and keyboard and monitor with you, using your hands as the input device. That's the basic idea of this project. So you can imagine this is your field of view. Now you're looking through the glasses, you're seeing your own hand, you're seeing the ground out there, but you're also seeing the overlay of the graphics. And in this case, it's a simple graphical interface where you're going to use your hand to move around these 3 icons and maybe select one, and then it'll go into a different mode perhaps. And you'll be able to get through some simple application just by moving your hand around as you're walking in the world. Or perhaps you're wanting to frame an image that you're about to take, or maybe say, this is the location of the bad guy or whatever, using 2 hands in this case. Or here's a situation for sort of a search and rescue kind of operation. Perhaps you've been rushed to a scene where there's some chemical spill, or there's a fire inside a building or something. So your system knows the architecture layouts of that building there. And so you can, in a sense, look through the building. You can have X-ray vision, and you can use your hands as a way of sort of navigating through that space and looking for, now, where is the room I need to get to? What's the path I want to go relative to where I am right now? So using your hands to manipulate in this sort of real-time rescue kind of environment. These are a few possible applications of this kind of work. So I want to show you just a little bit of bits of video here. This is the sort of output of the hand tracking aspect of this. So through the camera that's looking out in the world, we can see your hand and track it very robustly, indoors, outdoors, with lighting changes, etc. It's robust, all kinds of camera motion as you walk around in the world. It does a very good job of keeping track of where your hand is. At this point, as long as you're wearing a long sleeve shirt, but we'll fix that. Okay, so just to give you a little feel for the tracking, and now here's a little feel for using it in an application. So you're walking around your office or somewhere, you put your hand out so the system can see it, and the red dot will show that your hand is now recognized. Okay, I see a hand, now I'm going to track the hand in real time, and when I make a particular gesture, it brings up icons, and now I'm tracking the horizontal location of my hand so I can select perhaps one of those icons and do something. It's sort of a make-believe application here. Maybe we're starting some kind of remote system or whatever, make some selections, and then when I do a different kind of gesture, it will move into a new mode and bring up a new set of icons right there for me to work with. And there are some other applications there, but I'll move on in the spirit of getting you to lunch soon. So this project with the hand detection, tracking, and gesture recognition is actually available as open source software. If you search for hand view, you will find it. There are actually quite a few people using it now to do various kinds of, at least at this point, prototype applications in augmented reality. Okay, so that's one project. Another is sort of an extension of this, or something that fits in a little different way with this idea. That last project was basically just tracking the generic location of your hand in the image and looking for particular postures of your hand. This project is the other extreme of that, where we actually want to use a couple cameras and get a detailed model of your actual hand geometry. Okay, what are the joint angles and et cetera of your hand, so that we could do actually very fine-grained hand gesture recognition, things like that, maybe sign language understanding, or other kinds of applications where the actual postures of the hand matter, not just the general location of the hand. So we're actually using two cameras to look at the hand, and then essentially trying to match in a huge database that's synthetically generated of all possible hand configurations. It's not necessarily the intuitive way of doing this, but it turns out that it's quite quick computationally, and is perhaps at least better than some of the bottom-up methods, which might look for particular features and build models from there. So it's a very interesting exploration that we're doing right now in this approach to 3D full hand modeling. And this just shows an example where on the top left there are two images from the two cameras looking at the person's hand, and then these pairs of images here are actually giving us the top choices in our big database of what we think the parameters of that hand are. And up in the very top right there is the best choice, the #1 ranking retrieved result. And it actually is pretty close to what the person is actually doing. And from that, we actually know then exactly what the parameters of the hand are. Okay? So that's just a quick view of that more detailed hand modeling project. Facial expression analysis. So you're getting the idea that we like to point cameras at people as well as pointing them out towards the world and understand things about people. That's part of the technology for advanced human-computer interaction that we're interested in. So we point a camera at a person in various contexts to understand the facial expressions in this case. It could actually be just to drive an animated model, for Hollywood and such kind of animators, or it could actually be to analyze and say this person is smiling, this person's frowning, this person's happy, this person's bored, whatever, to enable other kinds of interactions based on that output. So this is actually a very hard problem, understanding facial configuration and understanding expression. Human expression is a very complicated matter, both from a sort of psychological and sociological point of view, as well as from really a technical point of view of trying to make sense of this malleable thing that we wear on our skulls. So what we're trying to do is basically take this large, very multidimensional problem and trim it down into fairly low-dimensional representations of faces, and then reason in these low dimensions where the smiles might be, as someone goes from neutral to smile back to neutral, or where the frown might be, or where the anger might be, or whatever, in various kinds of expressions. So just to show that we take people and nail their heads to the wall and make them do various kinds of facial expressions, and we can sort of show where along the, I guess, anger path, in this case, he is, and that, in fact, it's not just on the anger path, but it shows bits of disgust and a little bit of fear and sadness, etc. So we're trying to analyze expression. This just gives you a very coarse idea, but in this sort of fashion. And then we're also moving to 3D situations so that we can not just do it with frontal views of human faces, but actually do it no matter what orientation I'm at, and also to go from a model of one person that you've learned very well to a new person that you've never seen before through a generic 3D process. Okay, just a real quick note on another project that involves human-computer interaction in a different sort of context. The surgeon here is looking at the computer over there and telling his colleagues where to move the mouse and where to click. Very inefficient process that often results in the surgeon throwing up his hands, walking around the table, going over the computer, grabbing the mouse, doing it himself, and then going and washing his hands all over again so he can get back to the surgery. Not very good. So this is a collaboration with people at EPFL in Switzerland who are working with surgeons there. They're very interested in a scenario that lets the surgeon drive the computer directly, potentially through voice as well as through gesture, but they're working on the gesture part of it right now, using depth data, sort of a stereo camera, to figure out where the arms and head and torso of the surgeon are, and to provide fairly efficient ways for that surgeon to interact with the system. Okay, this is just a project on multimodal biometrics that I didn't have too much to say about, except that we're trying to integrate both multiple modes, like face recognition, fingerprint detection, keyboard typing, all sorts of things, and integrate over time to give an operator, for example, the best guess at any given point in time if the user is the one he or she claims to be. Okay? And there's a lot of probabilistic analysis involved in this. Fog screen. Rich or somebody, I think, earlier mentioned the fog screen, so I just wanted to quickly show you a couple of videos of this. This is a device that actually sends a thin layer of fog down from above with air currents on either side so it doesn't disperse too much, projects from projectors on both sides of that wall of fog, and it can be used as a display device. So you sort of see it from the side there. It's an immaterial display in the sense that you can walk through it, put your arms through it, you can sort of walk and look around. It's a different kind of display than probably you've ever seen before. This was actually invented by someone in Finland who came to do a postdoc in our lab, and what we've been doing is making this fog screen interactive. So the next video gives you a little sense of what that means. This marker is being tracked in the environment, and this person now is writing on the fog screen just by moving this marker around that he's holding. So it's a very compelling, I wish we could give you the demo today, but unfortunately we can't, but it's a really compelling experience to walk through and see this display that's unlike anything you've probably ever seen before. Okay. And then finally, the last 30-second project here is something in multiflash imaging. The general idea here is that we're basically using a camera with 4 flashes, not a single flash as is typical, but 4 different flashes that are positioned as such. And here's actually, this is the faked image. This is the prototype that we're actually doing it on. This one looks a lot nicer than this, but you know, what are you going to do? So what we get we take 4 images, one with each flash, of the same scene, and we get 4 slightly different versions. You can see from those top 4 images that the shadowing is a little bit different, right? You can take all of those images, take the maximum value at any pixel, and you come up with a shadow-free image up there on the top right. It looks like it has no shadow. Now what we can do, we can compare that shadow-free image on the top right with the 4 that we got. And essentially we can come up with, from this kind of a scene, we can come up with depth discontinuities. Okay, where in the scene are there sharp discontinuities in depth from the camera's point of view? And that is very different from changes in color or texture that typical edge detection algorithms will give you. Depth edges tell you something fundamental about the shape of the object. And that's actually very, very useful in a lot of areas. And so just real quickly, going from an image like this, which is the raw image, to what's called a non-photorealistic rendered version of it, is something that we can automatically do with this camera. Okay, it's basically throwing away a lot of the irrelevant detail and, in a sense, highlighting the stuff that someone in a user's manual might care about. A couple other examples there, going from the originals on the left to the newly rendered versions on the right. Again, left original, right rendered in different ways based on this multi-flash imaging technique. We've also applied it to medical imaging. So we're taking a laparoscope, putting 2 flashes instead of 4 on a laparoscope. And so we're able to actually give the surgeon some visual feedback in terms of where a discontinuity is in all this kind of bloody mess in there. Here's a little extra visual information to go around this corner here that might be hard to see otherwise. Reducing specularities, doing finger spelling recognition based on this kind of information from this image. And finally, we're actually applying this to stereo vision now, which is the idea of using 2 cameras, or at least 2 cameras, look at a scene and trying to get the depth of that scene from multiple viewpoints. It turns out that stereo, here's a typical image and a typical depth image from that. Along this depth discontinuity here, stereo tends to be really bad. The results of stereo tend to be very poor along that discontinuity. And the top 2 images here are typical outputs of stereo routines. And this is our output, which still looks kind of messy, but you could sort of compare various locations and see that this looks more like that image, which is the ground truth, than the ones on top do. So we're basically able to improve the stereo process by using this multi-flash technique. Okay? So basically there are a bunch of other things going on in the lab. That was just a real quick overview, but feel free to go to the website and you can see a bunch of other stuff there, get papers, et cetera, et cetera. So that's all I have. Thank you.